Oh, well, really, we did that in class. Oh, right, you weren't here. Yeah. So, you know that P is equal to P0 plus V0T plus 1/2. Okay. It's pretty fast. So, uh, the question is, what's V when P equals P0? Does that make sense? And so then you could use this equation, 2A times P minus P0 is equal to V squared minus V0 squared. And so 2A times P0 minus P0, that, goes away, is equal to V squared minus V0 squared. And so you get that V is plus or minus V0. When it's on the way down, you'd be dealing with the negative. So anything in free fall, if there's, if you're neglecting air resistance, when it returns to the starting height, it's whatever moving in the opposite direction at exactly the same speed as it took off with. Any other questions? Yep. Mm-hmm. That's right. That's when, so something, the candidates for something changing direction all occur when V is equal to 0.
Okay, but in that one, it's not solvable, right?
Oh, is that true?
Because it's sine of 4t equals -2, and sine has never been.
Okay, well, good.
Because then the next question moves off of that one, and I was like, wait a minute.
Oh, no.
That doesn't exist.
Okay, well, that'll happen sometimes. Let's take a look at that. Okay, so dv dt is equal to 2 cosine 4t. Velocity as a function of time is equal to 1/2 sine of 4t plus 1. So, right, that's impossible. Whoever wrote that question is a idiot, stupid idiot. You can't, yeah, that's impossible. So that was a trick question, an inadvertent trick question. So V of t is never 0. So there can never be a time that it changes direction. Okay, what was the next question? Anything else? Okay. Okay. A ball is thrown straight up into the air with an initial speed 5 meters per second from an initial height of 1 meter. How long does it take to hit the ground? How fast is it moving just before it hits the ground? Okay, so number 4. Yes. I think part.
It has
When
it changes direction.
Yeah, it's all about the object changing directions, and it never does because the velocity has to be 0 for something. Yes. No, acceleration can be, so like when you throw something up into the air, it starts out with a positive velocity, changes to a negative velocity, but the acceleration never changes. So if you think of the position versus time graph, so anything with constant acceleration is a parabola, and if it's concave up or concave down the whole time, then the acceleration never changes, if it's a parabola, but the direction changes when it gets to the peak or it gets to the bottom. Yes? No, G is just a magnitude. It's just 9.81 meters per second squared. And whether you use it as positive or negative, this has to do with your choice of positive direction. So if you choose positive up, which I said always do, then you use negative G. But in the equation, it would be written like this. Like P is equal to P0 plus V0 T minus 1/2 G T squared. Okay, you just put that negative, because G by itself doesn't have that negative. Any other questions about that one before I go back to 4? Okay, so 4. A ball is thrown straight up with initial speed of 5, initial height of 1. So we'll say V0 is equal to positive 5. P0 is equal to positive 1. Right. Thank you. How long does it take to hit the ground? And second, how fast is it moving just before it hits the ground? If you're comfortable if you feel pretty good doing these problems, then you don't have to worry about this. But if you're having some trouble figuring out where to go on these, you can sort of systematize this approach. Okay. So you can think of these problems like this. First, choose your 0 position, positive direction, and your 0 time. This one I usually just choose the ground or the lowest point in the problem. You don't have to do that. Hey, can you guys listen? The positive direction for these, I'm always going up. 0 time is at the start of the motion. Um, and then think about what variables you know and what variables you want to find. Um, and actually, let me add one more thing here. So 0 time, and then think about time t also. And both of these are sort of based on like where you call your time 0 and where you call your time t are based on when you know stuff and when you want to find stuff. Okay, so let's list out what we know and what we want. In this problem, our time equals 0 is going to be when the object starts at a height of 1 meter. Part A, well, both of them, we're trying to find when it hits the ground. So our time 0 is going to be when it's at 1 meter, and our time t is going to be when it hits the ground. And so let's think about what we know. There's only 1, 2, 3, 4, 5, 6. I think there's 6 possible variables, and we can just go through them. Like there's t, there's p0 and p, there's v0 and v, and then there's acceleration. And you can just step through those and think, do I know what those are or don't I, you know? And there's always one thing we're trying to find. So, okay, do we know time? Do we know the elapsed time between time 0 and time t? No, and that's what it's asking us for, right? So put that over here. Okay. Do we know the position at time 0?
It's 1.
Yep. And it's positive 1 because our positive direction's up and the ground is 0. Do we know the position at time t?
0.
0, yep. Do we know the velocity at time 0? Yep, that's given. You guys aren't looking at this problem, so it's hard to keep this stuff straight. But it said its initial speed is 5 meters per second up. So v0 is positive 5 meters per second. Do we know the velocity at time t? Nope, we don't know that. We want to find that in part B, but for now we don't. So I'll just leave that off of everything. Do we know the acceleration? Yeah, free fall problems. It's always just downwards at 9.81. Our positive direction's up, so down is negative. Let's see. So, no, we're going to use the first one I gave, that position equation for this one. But that's the one I mean, yeah. Yep. I don't know how I ordered them before, so that's the one to use, yeah. Yes. Okay. So first, anyone have any questions about these? All right, so now what you're doing is, a single equation you can only solve for one variable. So now, ideally, you're looking for an equation that has the variable you're looking for, otherwise you can't solve for it, and the other variables in the equation are all known, okay? If you don't have that, then what you need to do is use an equation that'll let you solve for an intermediate variable that you didn't know before. And then that intermediate variable has to let you find an equation where the one you want is in the equation and everything else is known. Okay, so the first thing we're going to do is look and see if there's an equation that has t in it and everything else in the equation is known. And you can see that the one that'll work for that is P is equal to P0 plus V0t plus 1/2 a P squared. T is in it, that has to be, and everything else in it is known. So this one will work. Yeah, exactly. That's right. In this case, you're going to have to. So 0 is equal to 1 plus 5t plus 1/2 times negative 9.81 times t squared. So 0 is equal to 1 plus 5t minus 4.905 t squared. Quadratic formula. So this is your A, B, C. And I think you guys all have just sort of basic calculators, right? Because they don't let you use, like in your math classes, you haven't been allowed to use graphing calculators, right? If you have a Texas Instruments type graphing calculator, it'll solve quadratic formulas for you and you never have to remember the formula. So anyways, solve that and you get, well, I guess we should solve that so we can go on to part B. Can at least 2 people solve that so that we have confirmation of the answer? Oh, you have it here, don't you? What number is this? 5?
It's number 4, A.
1.19, yeah. Okay, so T is equal to 1.19, okay, and then something else.
Like negative
4. Okay, negative blah, blah, blah. Yeah, if you ever get a negative time, that's the easiest case because we're never setting up problems where the negative time is meaningful. So you can reject that one and keep that one. Sometimes there'll be cases where you'll have 2 positive answers for time, or there can be cases. Like when that would occur would be, say that you're launching a ball from a cannon that's under the surface of the ground, and you want to know how long it takes for it to hit the ground. Well, then your final position is 0. But after you launch this ball out of the... Exactly. And so you just have to reason through the problem. Like what the equations don't know that there's like a stop and an end to this problem. They just think this thing's on a like never-ending parabola, And so you just have to think about where on this parabola represents the instant that you're looking at, In that case where you're shooting something from under the ground, you'd be looking for the second time the object is at a height of 0, because the first time it's just screaming by the height of the ground on its way up, you know. Okay, and then part B. How fast is it moving just before it hits the ground? So in this one, I worded it just before it hits the ground, which is kind of an indication that we're not worried about anything that happens when it hits the ground. But even if the wording says what's the velocity when it hits the ground, our equations can't take into account the object actually running into the ground. These equations only make sense while the thing's in free fall. And so a mistake people make pretty often is they think, okay, well, it hits the ground, the velocity is 0 there. But our equations don't know that the ground makes the thing go to 0 speed or what happens. It's just, these equations just give you the parabola. And so, anyways, when you're looking for when something hits the ground, you don't want to use velocity equals 0. That, if you use velocity equals 0, that'll tell you what's happening at the highest point. Okay, so for the second one, well, now we know if we use these same time equals 0, position equals 0, positive direction, then all the things we knew before we know now, and we also know the time. We're trying to find the velocity at time t, so now we can use this equation. V is equal to V0 plus AT. So V is equal to 5 plus negative 9.81 T. So V is equal to 5 minus 9.81 times 1.19. And it's going to be, so think about it this way for a second before we think about the numbers. You know, you just punch it into your calculator and get the numbers. But is it going to be, so it's on the way back down, so it's going to be a negative velocity. Anyone have any questions about that? Does that make sense? It's on the way back down, so velocity is negative. It's going to be somewhere around 5. Is the velocity magnitude going to be bigger or smaller than 5? And how do you know? Bigger, that's right. Yes, that's perfect. Yeah. So we know that when it reaches the height that it was launched at, it's going to be exactly the same speed as when it was launched. So when it's 1 meter off the ground, it's going 5 meters per second down. And then it falls another meter, speeds up a little more. So it's going to be like probably 5 point something. What do you get when you calculate that? 6.68? Okay. Yes. Right, you would get the same answer. The only reason we ended up using this one is we already knew the time because it made us calculate that. And if you have the choice between, okay, yeah, right, yeah, that'll work too. There's always multiple ways to work your way through these problems. But if you can ever use this equation, the V equals V0 plus AT, use it because it's the simplest one. You never have to deal with squares. You never have to deal with a quadratic formula. If anything, like I'd say the biggest pain of using an equation, like having to use the quadratic formula, is then you're going to get 2 answers and you're going to have to think about a reason to differentiate between the 2 answers. And if possible, you want to do as little thinking as you can, you know? Yeah. Thinking, do you know that 100% of errors come from thinking? That's true too. That's a pretty morbid fact, but that is true. Right. Wasn't it Descartes who said, "I think, therefore I am going to die"? Yeah, that's how I remember it. I'm not like a philosophy major or anything, but um, anybody else have any questions about this stuff? Free fall? Where do the free fall equations come from? They do sort of come from gravity. That is true. Yes, they. For our purposes, they like if you had to derive those, and you did on I think the previous assignment, you derive them from saying a as a function of time is equal to this constant a, and then integrating, right? So you could come up with these equations, but when you're using these equations for constant acceleration, this is sort of an approach for using them. Yes? Then, yes. You can't use these, so these equations, these equations are only valid constant acceleration. Okay? If acceleration isn't constant, then you just have to use the derivative relationships between acceleration, velocity, and position. So in a way, it's sort of odd that they chose to single out constant acceleration. Like, why didn't we single out linear acceleration? We could have done the exact same approach, done these integrals, and come up with a set of formulas for. It'd be a little bit more complicated, but the only reason we singled these out is because free fall comes up so often that we set these aside. Like, let's just remember these, and we won't have to derive them each time because they come up all the time. Because because it's a good approximation for stuff that happens pretty often. Yeah. Yes, that's right. What? Good, thank you. I hate it when people like don't agree with me. Like I say something, I go through the lecture, and someone's just like, "I think we're going to have to agree to disagree on this." No, that's never really happened, but that would be fun. I don't buy it. Sorry, I don't buy this. Actually, that totally happens in like astronomy classes and stuff, where they'll be like, and this is how we know that the Earth is 6 billion years old because we have, and people will totally just be like, I don't buy it. No, nope. I'm still gonna go with the 5,000 year old Earth. Any other questions on this? Okay. Well, this stuff is going to come up again very soon when we do it in 2 dimensions. So this stuff was all along a line, 1-dimensional motion. What? Yes. So. Well, so right now our equations only work for something that moves along a line. You actually could apply them for things where you know the path too, but I'm not really talking about how we would use it in that case. But now we're going to switch to things where, like, so right now our free fall problems are just, there's kind of three options, I guess. Things that can be dropped from rest, they can be launched straight up and come straight down, or they can be launched straight down. That's all that we can do. So what about like when you throw a ball and it travels in a parabolic path? So that's 2D motion, and that's what we're going to get into now. For what happened Saturday? You threw your Rubik's Cube? Like, you got 21 seconds and threw it? Ah! Oh, yeah? Mm-hmm. Oh. Oh, sad. So are you going to get another chance at that? Okay, yeah. Okay. You're going to kill it next time. Okay. I know you're thinking, that must be the end of class, but that's not true. No. Classes, we actually are just starting the material for this class right now.
Yep.
Okay. So, yeah, thank you. Okay. So now we're going to switch from one-dimensional kinematics to two-dimensional kinematics. What does kinematics mean? Don't look. Think. Wow. In Latin or something?
I mean, that's just like the Latin word. Word within the word.
Nice. I did not know that. Kinematics. Yes, very good. Oh, you looked. Yeah. So kinematics is describing motion without looking at the causes of the motion. Yes, I already said that.
Did.
Yeah, I just want you to, I'm saying it again because I want you to remember it. The reason I bring this up is because the kinematics is we're making a distinction between kinematics and when you do include the causes, it's called kinetics. Like, could they make that any more like confusing to, like, they sound exactly the same, but you know, not exactly. Just add ma, yeah. So the easy one has ma in it. Okay, so in 1D, at any instant, no. Yeah. What? In 1D, at any instant, the particle has two choices of a direction to move. Okay? Very good. Yes, that is correct. So the particle can... That's true. can move in two directions, and that's why, you know, so in 1D, a particle's here, it can go this way or that way. And that's why in 1D, the plus minus sign gives enough options to represent the direction, you know. It's either going in the positive or negative direction. In 2D, you know, the particle can move in infinitely many directions at any instant. So if that's the particle, you know, it can go there, 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 there. I mean, look at that. That's a lot of directions, and there's even more than that. That's 8. Yeah, if you keep turning it, those arrows can represent. Yeah, that's true. That's a good point, yeah. But so, you know, we can't use, even if there were 8 directions, the sign, the plus minus sign isn't enough to choose a direction. So we need a new way to, you know, plus minus sign won't do it anymore. Yeah, so we need a new way to represent directions. There probably is a way you could represent direction in terms of some kind of smell gradient, but that's not how physicists did it. And so the way that we're going to do it is we're going to represent directions with vectors. Have you guys used vectors at all in math? A lot? Yes. That's correct, they do. Okay, so a vector is a mathematical object with the two properties, magnitude and direction. And we'll always think of a vector as an arrow. Where the magnitude is the length of the arrow. And the direction is just where it's pointing. A common mistake when people are using vectors or drawing vectors on figures or whatever is to just show the line. But, you know, there's a fundamental difference. I see that all the time, you know. Yes. What? Yes. there's a fundamental difference between a line segment and a vector. A line segment only narrows you down to two possible directions. A vector chooses one of those two. So if you don't put the head on that arrow, we don't know if it's going down and to the left or up and to the right. Okay, so you need to draw the head on there. If you, in the syllabus, it says if you draw a vector without a head on it, you fail the class. Okay. No, not really. Don't do that. Okay, so let's take a 10-minute break, come back, and we'll talk about vector calculations and how to put numbers, how to deal with vector components and stuff like that. Okay, so we're going to have to do mathematical operations with vectors. So first, I'm going to go through how those happen graphically. So vector operations. This is a graphical approach. There are two operations we're going to do. The first is adding two vectors. And the second one is multiplying a vector by a scalar. You know what a scalar is? Yeah, or just a number. It couldn't be a variable too, but yeah. I'm not sure why they don't just call them numbers now that I think about it, but that's all a scalar is. But I'm going to call it a scalar because most of what I'm trying to do here is make you sound smart when you do your admissions interviews. I don't know.
I'm a scalar.
Scalar and all right, so first adding two vectors.
Yeah,
well,
negative.
Yeah, you can think of that as multiplying, multiply 1 by -1 and then adding. One thing to notice about this, by the way, is that these operations can be done without defining a coordinate system. The way we're going to do most of, basically all of our calculations in this class is by breaking vectors up into components, but you can't represent a vector in component form until you choose a coordinate system. So people call this stuff coordinate-free vector calculations, and they call those, I don't know, they require coordinates. So these are independent of coordinate system. Okay, so to add two vectors, you first put the vectors head to tail. It's fine to move vectors around as long as you don't change their direction, because they don't, they have two properties and none of those is location. So put the vectors head to tail. And then the resultant vector that's the sum of the two vectors, goes from the free tail, the tail that's not touching the other vector, to the free head, the head that's not touching the other vector. So if you're adding this vector plus this vector, put the tail of one at the head of the other one, and then the resultant vector goes from the tail that's not touching anything to the head that's not touching anything. So the red is the resultant. Why did I choose to do them in that order? I could have just as easily chosen the other order, right? If I chose the other order, put the tail of the first one at the head of the other one, I would have gotten the exact same resultant.
That's not how vectors work.
Yeah, I don't know if I can come up with a better answer than that. That's not how vectors work. If I don't know anything about how vectors were discovered, but I do know that, like, how people started coming up with the way these things work. But I do know that if you measure vector physical quantities and you do operations with these definitions, you get things that make, like, all of the measurements that you take work out, you know. If you measure the resultant, you get the same as, so in that sense, you can say it's like a experimentally verified, you know. But so notice that order doesn't matter. How would you say that in your college admission interview? Vector addition is that really? I would say commutative, right? Order doesn't matter. So vector addition is a commutative operation. And then the other thing that we're going to do with vectors is multiply a vector by a scalar. And so I'm going to break this up into, so what if you're multiplying by a negative scalar? We'll just always think of that as multiplying by a positive scalar and then multiplying by a negative one. So multiplying a vector by a positive scalar changes the vector length or the vector magnitude by a factor. Why don't you say multiplying the vector by a positive scalar m changes the vector magnitude by a factor of m. Okay, so if you multiply by 2, magnitude is doubled. If you multiply by 0.1, the magnitude is 0.1 of what it was before. The direction stays the same. So 2 times the vector drawn there is equal to, there's one of them, there's 2 of them in the same direction, and so combined effect is this. Any questions about that? And if you're multiplying a vector by -1, keeps the magnitude the same, and just switches the head and tail of the vector. It just switches the direction. So -1 times this vector is equal to, the magnitude stays the same, and so you get that red vector as an output. And so you can combine these. So let's say we want to multiply -0.5 times the vector like that. Well, we'll get a vector that has half the magnitude, and then it switches directions. So there's the -0.5 times that original vector. Any questions about those? Have you seen all that stuff before? Okay. So now usually we're not going to use this coordinate system free. We'll choose a coordinate system. And then do operations using vector components. Let's see. Okay, so the way components work, so say this is your vector. Move the tail of your vector to the origin of the coordinate system. It has to be the tail. And then break this vector up into the sum of 2 different vectors. One that's parallel to the x-axis and one that's parallel to the y-axis. So in this case, that's a vector parallel to the x-axis. Parallel. And then there's a vector parallel to the y-axis. And the vector is the sum of the two component vectors. Coordinate system free. So if you, what I mean by that is if you started with those two vectors and did the vector addition this way, you calculate that resultant. And then you could calculate the components of these things in a coordinate system like this, or like this, or like this. And this way of doing it would work in any of those coordinate systems. Okay? So doing this didn't depend on a choice of coordinate system. We didn't change anything about our approach. Components totally, right from the start, depend on what your coordinate system is. If I chose, if I had chosen this coordinate system to be like this, I would have had to choose two totally different component vectors to add up to that. Okay, even though the vector is still the same thing. So the vector is the sum of the two component vectors. Since we know the directions of those component vectors are parallel to the axes, there's no reason for us to write them as vectors. We can just give the magnitude and the sign along each one of those. You know, like this vector parallel to the x-axis, we can just represent that by the magnitude of this, and with a negative indicating it's in the direction of the negative x-axis. And same with this one. We can just represent it. This is the magnitude and a negative because it's in the negative y direction. There's a couple ways you can represent these. If you find the counterclockwise angle from the positive x-axis to the vector, remember, so this will be wrong if the tail of the vector isn't at the origin. You'll get the wrong number. So remember to put the tail of the vector at the origin. And let's call this angle theta. Okay. Then the x component is the length of the vector times the cosine of theta times a unit vector in the direction of the x-axis. The y component is L sine theta times, have you seen that I and J notation?
Yeah. It's a
Some.
hats.
Oh yeah, so you know what if you put a jaunty hat on a vector like that, you know what it means? I suppose you could use it for that reason, but it might confuse some people because people usually use that in a vector that has a unit vector. Have you all talked about unit vectors before?
Yeah.
They're just vectors that have been normalized.
Yes, that's right.
You
So
divide
this
the
means,
vector by its-
so basically, if you have a unit vector, if you ever see a vector with a hat, you can think of that as indicating a pure direction. Okay, this thing doesn't have any length. It has its length is 1. So whatever you multiply it to, that's going to be the length of the vector that you get out. So this is just saying, take this value and put it in the direction of the x-axis. Okay. And the other one says, take that value, put it in the direction of the y-axis. Yes?
Why do we need to do that? Because we are dealing with outcomes data. Why do we need to use it?
Because those are vectors. You're adding those two vectors to make it equal to your total vector. And so, really, I think that's probably not even that it seems like a big distinction, but practically speaking, it really isn't. I'm just saying that in order to get this vector out, you have to add two vectors. And the way you make these things into vectors is you take a value, multiply it times this direction, and you take this value and multiply it by that direction. Okay, so let's, for example, calculate the components of a vector with a magnitude of 10 that makes an angle of 20 degrees from the vertical. And we'll put it in a coordinate system. Let's put it in the one we're used to. And actually, then let's put it in let's do it in a wacky one. Okay, so first, the one that we've always been familiar with. So I'm going to take this vector without rotating it and just move the tail to the origin. So this angle is 20 degrees. And the magnitude is 10. So what's the counterclockwise angle to get from the positive x-axis to that vector? Yeah, so it's, if you go counterclockwise, you can go 90, 180, 270, plus 20 is 290. Or you could go clockwise and call it a negative angle, so that would be negative 90 plus 20, so negative 70. So theta is equal to 290, or you could also say theta is equal to negative 70. It doesn't change anything. And so the x component is 10 times the cosine of 290, which is 3.42. And the y component is 10 times the sine of 290, and that is negative 9.40. Yes. To see stuff before? Okay, I'm going too fast. So now for part B, we still have the same vector, but the coordinate system now, the x-axis is this way, the y-axis is this way. This angle's 20 degrees. And now what's the counterclockwise angle from the x-axis to the vector? It would be, so you could go 90, 180 plus 20, so 200. Or you could go clockwise, negative 90, negative 180, backtrack 20, so negative 160.
Why is it?
The magnitude of the vector is 10. I gave it up there. Yeah.
Hold on.
Yeah, that's L. That's the magnitude. So theta is equal to 200, yep. Or negative 160. And so the x component is equal to 10 times the cosine of 200, and the y component is equal to 10 times the sine of 200. Well, this is negative 9.4. This one is negative 3.42. So notice that this is what's different between this approach and that coordinate-free notation, is that if you think of those components as the identity of that vector, okay, this is what we're going to use for calculations regarding that vector. Changing the coordinate system fundamentally changed our representation of that vector. That's different, yes. You can always think of these, well, that's like the next thing I was going to say. You can always think of the components of the vector as being equivalent to the coordinates of the head of the vector. So if you think of just figuring out the coordinates at this point, here we're in the third quadrant, so they both have to be negative. Okay. Here they're in the fourth quadrant, so you have to have positive x, negative y.
Okay, so wait, not only did x and y change, but y became negative x?
Right.
Oh, so it has to go, it still goes counterclockwise though, right?
Yeah.
Does
Yep.
it always, will it always go counterclockwise?
Yes, or if you go clockwise, it's negative. Yep. there are two ways to represent vectors in this component form. The first one is that this vector, I call it U actually, because V we'll use for velocities. The first way is to say the x component of U times this unit vector in the x direction plus the y component of U times the unit vector in the y direction. And so in the example we just did, we would say U is equal to uh, 3.42I minus 9.40J. And the second way to do it is U is equal to UX, UY as a column matrix, so in square brackets. So for example, U is equal to, that's the vector gong. We're going to play that, the vector gong, whenever we write a vector in this form. There actually used to be a bell here that was even better as a vector gong. So in this notation, you would write this 3.42 negative 9.40. Okay? So those two forms are equivalent. They mean the same thing. You can think of this matrix notation as saying that you multiply the first one times the x direction and the second one times the y direction. Notice. So let's say finding the components of a vector.
I missed it.
Is exactly equivalent to finding the coordinates of the vector's head. I said vector.
I tried.
I know. You had one job.
I'm ready.
This is the mind blown guy. So
If this whole physics teaching doesn't work, you can always go into like
yeah, there's a actually isn't there a famous painting that looks almost just like that? Yeah, if only
Also Home Alone.
he hadn't beaten me to it. Oh yeah, in a movie, Home Alone. That's true. So that's what we're doing when we do this finding the components here, you're doing exactly the same thing. Just putting the tail of the origin and then finding the coordinates of the head of the vector.
Scares me.
We should really get a legitimate gong for this. Oh, you do? Can you steal it? That's not stealing it if you ask. Okay, so now we're going to do these two operations again with components. Oh, finding the components of a vector is exactly the same thing as putting the vector's tail at the origin and then finding the coordinates of the vector's head. And that's something you've done a million times. So if you think about it that way, it's not new at all. Yeah.
Does Victor have a tail?
Yes, he does. I didn't draw it, but
He's a little short.
yeah, he has a small magnitude. Okay, so the first operation is adding two vectors. It's worth it. Okay, so if you're adding the vector AB, and the vector CD, the resultant vector has an x component of A plus C and a y component of B, exactly, B plus D. That's the first rule of comedy, of vector comedy. So notice that again, just like with coordinate-free notation, order doesn't matter, you know, because C plus A is equal to A plus C. So for example, if you have the vector 1, 2, and you add it to the vector negative 8, 4, the resultant vector is negative 7, 6. And if you think about it for a while, it'll make sense why this is true. But if you really carefully chose a coordinate system, using a ruler and a protractor, drew out this vector, same thing for this vector, and added them up using the coordinate-free rules for vector addition, you would get exactly this. Isn't that interesting? If you think about it, that'll make sense. If you think about how that works, but the second operation, what would you guess the second operation is? Yes, multiplying a vector by a scalar. This is going to be the best excuse ever for No, I was hoping to do better on the AP test, but I was so busy in class beating the vector gone. I couldn't take good notes.
I got this stuff. I'm in vector calculus.
Yeah.
I think I'm
Yeah, right. Okay, so
can devote my full attention to the vector.
good. So if you multiply the scalar c to the vector AB, that was a good one. You get the output vector CA, CB. So for example, if you multiply -4 times the vector 6, -2, you get -24, +8. Who's with me? No, only me.
No, that's way too long. I'm only doing it for this class.
Okay, only this class. I think that's a good decision. Yeah. Okay, so you can combine these things. So, like for example, 2 times the vector 5, 1. Oh, it was really dead. -0, 4 is equal to 10, 2, -0, 4. So it's equal to 10, -2. And notice that you can do all these vector operations as 2 scalar equations.
We said
Yeah, each one of the components is multiplied by the number. 2 times what? Yes. Yep. These vector operations can be done as 2 scalar operations. So, oh yeah. For example, yeah, it's like phonetic. This thing above is the same thing as saying 2 times 5 minus 0 is equal to 10. 2 times 1 minus 4 is equal to -2. You get the same things out. So a lot of times we'll be doing vector operations, but it won't be like totally obvious in the way we're doing the calculations, because instead we'll break it up into an x equation and a y equation. Any questions? Okay, see you Wednesday.
Okay, we good.
Yeah, no more vectorgon after that. Yeah. Okay, be quiet. Oh. Yeah, right, the snow. I wonder if we're going to get out early here.